Hi, I'm Amir Hossein Mirzabozorg, and in this video I want to talk about too many atoms made for disincrement error in Abaqus, and then I want to talk about the ways of resolving this error. In this video, I teach you the ways of resolving too many atoms made for disincrement error in Abaqus. This is the table of content of this video. First, I explain the Abaqus structural solvers. Then I explain sources of nonlinearity in the analysis. After it, I explain the method of solving nonlinear problems. Then I explain the primary cause of too many attempts made for disincrement error. And finally, I explain the ways of resolving too many attempts made for disincrement error. Abaqus has two structural solvers, Abaqus standard and Abaqus explicit. Abaqus standard uses implicit methods for solving nonlinear problems, and Abaqus explicit uses explicit methods for solving nonlinear problems. Each of these solvers has some steps, and you can use steps to solve your problems. For example, Abaqus standard has a static general, dynamic implicit, coupled temp displacement steps, and all of these steps uses implicit methods for solving nonlinear problems. Abaqus explicit has dynamic explicit and dynamic temp explicit step for solving nonlinear problems. These steps use explicit methods for solving nonlinear problems. These steps are some of the famous and useful steps in Abaqus. First, I want to explain the sources of nonlinearity in the analysis. These are sources of nonlinearity in the problems. When you want to simulate a phenomena or process in Abaqus by using FEM. Nonlinear material, nonlinear boundary conditions, and large deformations. That is nonlinear geometry. For nonlinear material, I can give you these examples: hyperelasticity, plasticity, and damage. If these cases are in the problem will be nonlinear. For nonlinear boundary conditions, I can give you this example: contact. If the contact is in the simulation will be nonlinear. And for large deformations, I can give you this example: metal forming analysis, like deep drawing, direct extrusion, and reverse extrusion, for example, or forge process. That all of these processes has large deformations, and so all of them are nonlinear. Now I want to explain the nonlinear material case in sources of nonlinearity in the analysis. This is the complete diagram of nominal stress versus nominal strain of metals. This part is linear elastic, this part is plastic, and in this part damage occurs. If the simulation goes just in this part, the simulation is not nonlinear because the material is linear elastic. But if it goes to this part and this part, the simulation will be nonlinear. And this is the complete diagram of nominal stress versus nominal strain of hyperelastic and rubber-like materials. And all of the diagram is nonlinear. And it doesn't have a linear part. And if there is hyperelasticity or rubber-like behaviors in the simulation, from the start of the simulation, it is nonlinear. Now I want to explain the nonlinear boundary conditions. Nonlinear boundary condition is a type of boundary condition that varies with time, like this simulation. In this simulation, the load increases and this beam deflects. This beam deflects until it goes to contact with this barrier. And contact is a discontinuous phenomenon that makes it nonlinear. The occurrence of contact between the tip of the bar and barrier makes this simulation nonlinear. But before contact, this simulation is linear. But after occurrence of contact, the simulation will be nonlinear. And I want to explain the large deformations that is one of the sources of nonlinearity in the analysis. Assume a bar that we apply a concentrated force on tip of it. By increasing the load, the bar deflects until this position. You can see that after some time, the angle between this component that is normal to the tip of the bar and the direction of the applied force increases, and it increases until that the size of this angle is more than 6 degrees. And then we cannot assume this angle small. And then the decomposition of the applied load to a normal component and tangential component will be important. And this is one of the meanings of large deformations or nonlinear geometry, that you cannot decompose it to just this component because of the small size of this component. After large deformation, this component will increase and then you cannot assume it's zero. Nonlinear geometry includes two cases: large deformations and rotations and pre-stress. Pre-stress is a phenomenon that is categorized in nonlinear geometry. The main idea of solving nonlinear problems is dividing problem into several increments and solving them respectively. In fact, for a nonlinear problem, we cannot solve the problem in one increment. We must solve it in several increments. And in Abaqus, the number of increments depends on the solver and step settings. This is the diagram of load versus displacement. And for example, in increment I plus 1, just this fraction of load will be applied to the system. In fact, this fraction of load will be added to this part, and then the total force will be applied to the system, and the new displacement and stress and strains are calculated. For solving nonlinear problems, Abaqus standard uses Newton-Raphson method. This method is so famous, and in the courses for numerical calculations, this method will be taught. This part is passed from the beginning of the problem to the end of the I increment. The fraction of the load will be calculated from this formula. Delta T divided by T total multiplied by P total. We have T total and P total in the settings of the Abaqus. We specify them, and the solver will determine the size of delta T, and then the delta P will be calculated. This formula will be used for both of the force control and displacement control loadings. If the loading is force control, we have fraction of force and the total force, and for the displacement control loadings, we have fraction of displacement and the total displacement. And now I want to explain the method of determining the attempts for solving nonlinear problems. Please notice that one case is iteration and the other is attempt. They are different. For example, in increment I, Abaqus chooses the size of the delta T, and then by using the Newton-Raphson method, it iterates until it finds the converged solution. But if after some iterations it doesn't find the converged solution, it will cut back, and we have one unsuccessful attempt, and the second attempt will be started. This is attempt 1. This is the size of delta T, and this is cutback 1, and this is attempt 2. In attempt 2, the size of delta T will be divided by 4. And then it will be started. If the solution is converged, Abaqus will start the I+1 increment. But if the solution doesn't converge, Abaqus will cut back again and it will start the attempt 3. And the delta t of attempt 2 will be divided by 4. We have another 4 in this part, and 4 multiplied by 4 will be 16. And the third attempt will be started. If Abaqus finds the converged solution, the I+1 increment will be started. But if it doesn't find the converged solution, the third cutback will be done, and then the fourth attempt will be started. The default maximum allowable number of attempts is 5, and the default maximum allowable number of cutbacks is 4. This is a picture of the job monitor dialog box, and in this column the number of attempts will be showed to you. For example, in increment 6, 7, 8, 9, and 10, the solution is converged in one attempt. But in increment 11, we have 5 unsuccessful attempts, and then the solution is terminated by the too many attempts made for this increment error. You know that the first way for resolving this error is to increase the parameter IA. Parameter IA specifies the allowable number of attempts, that the default number is 5, and you can increase this number. Now I go to Abaqus to show this dialog box to you. This model is a model for simulating the performance of a cohesive zone, and this is a simulation of DCB test. DCB is double cantilever beam. In step module, I go to Other, General Solution, Controls, Edit, Step 1. You must choose Specify, go to Time Incrementation tab, select More 1, and this is IA. For this simulation, I increased IA to 30. This is the first way for resolving the too many attempt error. Now I want to explain method 2. if you use Abaqus standard solver and there are contact interactions in the simulation, you must use a finer mesh in surfaces that are in contact with each other. For example, this is a simulation of direct extrusion, and I simulated this problem in axisymmetric space. And you can see that in this part, that the variation of the surface of the die is a lot. I used a finer mesh than this part or this part, because this part is a line, but this part is a curve, and you can see that I used a finer mesh. The third way is using dynamic steps instead of a static general step. For example, it means that you must use dynamic implicit or dynamic explicit steps. The solver of dynamic implicit step is Abaqus standard, and the solver of dynamic explicit step is Abaqus explicit. For example, if you used a static general step and then the too many attempt error occurred and you used method 1 and method 2 to overcome this error, but it doesn't work, you can change and replace your static general step to dynamic implicit and dynamic explicit. This is the dynamic implicit settings dialog box. Dynamic implicit step is developed for solving nonlinear dynamic problems. By choosing quasi-static for application, Abaqus standard guarantees that the problem will be solved in the form of quasi-static. Quasi-static analysis means that the participation of inertial forces or kinetic energy is very little than the participation of other forces and internal energy. Since the dynamic implicit step considers the effect of inertial forces in the model, the chance of convergence in very nonlinear problems will increase because the consideration of inertial forces terms in solving the equation helps the stability of the problem. The inertial forces term in the equations is m multiplied by u double dot. If again you encountered the too many attempt error, you must use dynamic explicit step. But there will be a problem. The problem is that the typical time increment size of explicit solver is 10 to negative power 6 or less. Because the time period of a static or quasi-static analysis is usually equal or more than 1 second, usually more than 10 to positive power 6 increments are needed to solve the problem, and it will take a lot of time even with parallel processing. For overcoming this problem, the loading rate technique or mass scale technique must be used. Notice that you can use dynamic explicit step or Abaqus explicit solver for solving quasi-static or static problems that are very non-linear. But by using loading rate technique or mass scale technique, you can decrease the time of the simulation. The time of the simulation is not the time period. This is the cost of the simulation. For example, for simulating a deep drawing process, if you don't use loading rate or mass scale, the cost of the simulation will be 5 hours. But by using mass scale or loading rate, the cost of the simulation is 2 hours. And this is very important for industry or the head of the project. You can contact me by my Gmail or phone number by using Telegram or WhatsApp. And our services are one-on-one tutoring on Skype or WhatsApp and high-quality simulations for thesis exercises and industrial projects. I hope that this video was useful for you. See you soon.